Welcome. I'm Cyril Arter from KTH, and I'm going to talk about model-based testing in this video. You may all know unit testing. On this slide you see some code for JUnit. In unit testing, we define how test cases work step by step. So if I have a system where I can take a step to the left or to the right, I can write different sequences of test steps as unit tests one by one. Each test then initializes the system, performs some actions, and checks if the resulting state in the system conforms to the expectations. Now, this is quite useful because it automates test execution. But we still have to write this test script step by step. So sooner or later, you will ask yourself, can this be automated as well? And yes, it can with model-based testing. We no longer write the test code line by line in model-based testing, but instead we define an abstract model that includes the potential behavior of thousands or millions of possible test cases, and then we take this model and transform it into concrete test cases. These test cases can then be output as a table of tests, or they can be executed directly in online testing. So we directly take the result of the transformation and apply it to the system. For this to work, the model has to contain a formalized description of the system behavior and ideally also some notion of what the expected state or output should be. And then the transformation tool takes this model and generates test cases. When we write such a model, we are not at the same level of detail for a test model compared to having to write a system model. A test model only has to describe what happens in the system. So in a sense, the model takes the role of the environment and it describes what kinds of actions we can perform on the system under test or SUT, and what kinds of results come back. And in this presentation, I'm mainly considering API or interface testing, but this can also be applied to other types of interfaces. If you have a system model where we want to provide a full verification, we also have to consider how the system actually performs the action. And that requires a lot more detail in the model. A test model is good to generate test cases because it only has to represent the environment and the behavior at the summary level. And a system model that is more detailed can be used for full verification, for example, model checking or theorem proving. Both have their place, but I'm focusing on the simpler, more lightweight test model in this presentation. A key challenge when we write a model is to keep it simple, but to still reflect all the interesting behaviors of the real world. So the model has to have enough detail to create interesting test cases. And how do we do that? One way of modeling aspects of a system is with so-called property-based testing. In this example, I show ScalaCheck. And with property-based testing, we try to describe what happens if we perform a certain action or two actions on the system or on an input. In this example, we see if I reverse a list twice, we go back to the original list. And we also see in the second property, if I add one string to another one, the result ends with the second string. You can see that I don't describe the exact result. So I could have a reverse operation that does nothing, and that would also fulfill the first predicate. Or I could have a concatenation operation that doesn't take the first half of the string. And I could also pass that test case. So writing good properties is an art. If I have these properties, I can then put in random data, and hopefully I have properties that are strong enough to detect problems if I throw enough data at it. So if I throw enough data at the system, then hopefully with 100 test cases, I find one input that generates a test failure if the property is strong enough. This type of property-based testing, and with ScalaCheck in particular, is good at testing stateless functions. And there are also advanced features that allow you to use the test generation in a more effective way. Now, if we think about automating tests, the question arises if we should try to write individual test cases or generate them. So should you stick with JUnit or go to this new model-based testing? And these approaches are really complementary. Usually you start with individual test cases with unit testing first. And then, if there is a component of the system that has a lot of behaviors with slightly different inputs or slightly different actions, that's potentially the time to start using model-based testing. This can augment unit testing and produce a lot more test cases than what's achievable by writing tests one by one. And finally, you shouldn't forget random testing, which is completely unguided and has no output oracle. It is fully automated and therefore has an even bigger coverage of the input state and can also be useful to find crashes or memory corruption or other problems. If we look at the overall spectrum between these different approaches in testing, and if we also look at grammar-based testing, which is a very specific model that only has valid or invalid input in the model, then we can see that unit testing is the most precise way, but we have to write each test one by one. And completely random testing is fully automated, but we lose a lot of precision because we have no idea about the result. So to summarize, unit testing automates test execution, and model-based testing automates test generation. But writing a good model is challenging, in particular if we want to verify the output. So both of these approaches are complementary and should be used together and not instead of each other. Now, if you like to try out model-based testing, then I encourage you to try out the tool Modbat. Modbat uses a domain-specific language or DSL based on Scala, which models what's called an extended finite state machine. So we have finite state machines with states and transitions, and in addition to these states and transitions, we have variables and expressions where we can track extra state in the model, not just what's in these bubbles, but we could have, for example, a counter. And we can also use these values in function calls and use them to verify the result. Modbat comes with the full source code and the tutorial, which you can find on the wiki, which also has instructions about how to build Modbat. The workflow of Modbat is that it takes a test model and compiles the test model with its own library that defines this DSL. As an output, you get Java bytecode, and the test driver then takes this bytecode of the model together with the actual system and executes tests against that. And as a result, you get a report about failing test cases, and you can also use these test cases by replaying them for further analysis. The first part of the tutorial, which I'm going to explain you here, is a simple list model. In this simple model, we define the operations to add elements to a list and remove them and check the size of the list. Because we want to interface with a real data structure, we actually create one instance of the real list in the model. We then define an operation that adds a random number between 0 and 9 to the list and also maintains count of how many elements we have in the list. Further down, we define a clear operation that deletes everything in the list and resets the count to 0. On the next slide, we see how we define a remove operation. We choose again an element at random, and we expect the size of the list to go down by 1. And finally, we have an operation that checks if the size in the model corresponds to the actual size of the list. In this case, we don't need any more detailed state, but we choose just one of these 4 operations at random, step by step, and then build up complex test cases through a sequence of these steps. Now, if we run this model and generate just 5 test cases, we already have 5 test failures. The tool also shows you the random seeds that were used to produce these test cases so you can replay them later on. And The way you analyze these tests is that you look at the error message, in this case the assertion error, and you repeat the test and look at what steps were taken to produce the failure. In this case, the test consists of 4 steps. I first add a number, in this case the number is 1. I check the size, and the size check succeeds, so the actual size is 1 and the predicted size is 1, 2. And in the next step, I remove a random number. In this case, I try to remove number 4. And then finally, in step 4, I check the size. And my model predicts size 0, but the real size of the list is size 1. And then I have to think if this is because of a problem in the model or of a problem in the list. And you can try this yourself. You will find all the information that you need on the GitHub page and the wiki, and the tutorial will guide you through this step by step. And just as a highlight, with a more advanced model, we found a real bug in the array list in Java 8, which was later fixed. So it is really possible to find deep bugs in real code with such model-based testing. Thank you for your attention.